Good evening, everyone. My name is Aditya Sharma, and this is Power Plant System Engineering course being conducted by Department of Mechanical Engineering, IIT Guwahati, under the NPTEL program. And we are into the fifth week of this course. Theme for the course, again in this week, is vapor power system. So second part of it. And the instructor for the course is Professor Niranjan Sahu from Department of Mechanical Engineering, IIT Guwahati. And I am a research scholar from Department of Mechanical Engineering, IIT Guwahati only. So we shall wait for another couple of minutes, and after that we shall start the today's session. Okay, so I shall start today's session. So, in this week's content, we have gone through performance analysis of steam turbines first, and then we were introduced to steam nozzles. Okay, so one by one, we shall see these lectures. There are three lectures in this week's content. So the session will proceed the same way. One lecture and then questions corresponding to that lecture, and this way we shall move ahead in our session. So let's see the topics of lecture 10, that is performance analysis of. So performance in this lecture, first topic is the heading only, the performance of steam turbines. So this topic basically is a recap of the previous knowledge that we have acquired in the previous lectures of this course, right? Where we discuss about how we use impulse turbines in our early stages, and then we switch to reaction turbines in later stages where the pressure we have to deal with is less. Okay. So discussion around that has been done in this topic, and then one parameter reheat factor is there, right? So reheat factor basically is so this is your reheat factor. What basically this is, so if your expansion from the steam turbine is taking place in steps, right? And we have used a reheater in between of the expansion, right? So the expansion will take place in, let's say, two steps. So if we consider the expansion to be isentropic from your place 1 to 2, if it is moving, right, in single step, and from 1 to 2, if it is from pressure 1 to pressure 2, it is moving in two different steps. So in that case, these two different scenarios, how they fare out. So this has been quantified using this reheat factor. So the numerator is for the different steps. You accumulate the enthalpy drops for different steps, and the denominator is the single step if the expansion takes place in just a single step, right? So this is your reheat factor. Then one very important topic is axial thrust, right? So maybe I'll show you one diagram from previous. tutorial that I had drawn, right? So this is that diagram, right? So let's say this is a moving blade, right? So these blades are moving blades. These blades are moving blades. So steam will enter from here, it will go like this, and it will exit like this, right? So the function of the steam is to rotate this, right? In this direction. Rotate this shaft in this direction. But then at the, if let's say this is your inlet of moving blades, this is your exit, right? So because of the pressure differences at the inlet and exit, so we this your whole shaft rotor will experience some force in axial direction, right? So this is one thing that is not required in steam turbines, right? We want the rotor to remain at its place only, right? Otherwise, it will create wear and tear in the turbine only, right? So this is your axial thrust, right? And we try to avoid this axial thrust. Okay, right. Then the next topic is design aspects of steam turbines, right? So here discussion has been done on blades. Yes, steam turbine blades. So basically the lengths of blades. So we have discussed that the blade lengths for impulse turbines are shorter and for reaction turbines they are lengthier, right? Because in reaction turbines we don't want pressure leakages. Okay, so these factors, and when we this has also been discussed that when we try to draw the velocity diagrams, we just uh, take one blade velocity only, right? But if you see the whole blade from the center of rotation, right, from the axis, if you see the with the radius, right, because velocities are omega, right? So omega is same for the whole blade, but then the radius changes, right? As we move towards tip of the blade, its radius changes, and which eventually changes the blade velocity. So all these things need to be considered while we are designing our blades, right? All right. Then the last topic in this lecture is losses in steam turbines. So, what is the cause of these losses? So, we shall see. Okay. So, first is your supersaturation. So, I'll first draw and then supersaturation has also been discussed in your lecture 12. That is on that is second part of nozzles, right? But we will discuss it here only. So this is your saturation line. Okay, vapor saturation line. This is your sum pressure P1. This is your sum pressure P2. Okay. And let's say this is expanding from here to here isentropically. And in actual, if you see, this is expanding this way, right? A, let's say this is B, this is 2. So if you see the process from state 1 to 2, right? The expansion is taking place. And in between there is point A, right? That falls on the saturation line, right? And after that, your vapor starts condensing, right? Ideally, it condenses. And this is your superheated state. But what happens is, while the steam is expanding from 1 towards 2, it reaches A, it directly doesn't start to condense. Okay. So till point B, it remains in this superheated state, right? And this and after this B point, it starts its sudden condensation, right? And this region from A to B is known as supersaturation region. Okay. So this super saturation somehow leads to losses in the available energy, right? And that is why we are discussing it under losses in turbines. So this is basically super saturation. We call it under cooling also, right? Yes. Okay. Okay. Then is your fluid friction, right? So I'm discussing losses and friction of lecture 10. So different types of losses have been discussed in your fluid friction, right? So also fluid friction is a major cause of losses in a turbine, right? So if you see your nozzle, the friction in nozzle leads to your losses, right? And then there are different types of losses like fanning losses, admission losses, blade windage losses. So blade windage losses are basically because of eddies that the blades face, right? And then there are losses because of the uh, based on the fact that whether your steam is laminar or turbulent. So if your steam is more turbulent, the losses will be high, right? So this is your fluid friction. Then leakages, right? So we have steam with some pressure, right? And that passes through your steam turbine from your boiler. But in between, if there are losses in this steam, right, there are leakages. So this leakage will lead to reduce in your this will lead to your pressure drop, unwanted pressure drop, and eventually which will lead to reduction in the available energy, right? So this is not required, right? And then is your moisture. Moisture is one important factor. So what happens in your steam turbines, your steam, if the steam is not in its dry state, right? If some percent is wet, in that case, the water droplets, right? There will be exchange of momentum because of these water droplets, right? And this will lead eventually to loss in the energy, available energy, and eventually the work output that we are obtaining from the turbines, right? So moisture is unwanted. All right. Okay. And one term or one phenomenon has been mentioned in your lectures, that is wire drawing, right? So basically, this is blade erosion as a result of impingement of water droplets. So when your water droplets impinge on your blades, right? So this leads to kind of wire drawing on your blades. Okay. So all these are things that are not required in your whole turbine process, right? So this was moisture. And then there are miscellaneous losses. Losses like when there is transmission, right? From turbine, we want to generate electricity, right? So your generator, how efficient that is, right? And all the bearing arrangements for the movements or passage of the energy, right? So losses in that, mechanical losses, right? So all this has been discussed in your miscellaneous losses. So after that, we shall see some questions based on this lecture. So this is first question. So please read this question and try to answer this. The question says that the ratio of total individual isentropic enthalpy drops to the enthalpy drop of a turbine section or the entire turbine is called as reheat factor. So whether this is true or not, please try to answer. And in the meantime, maybe I can try to find out. If I have drawn a reheater, yeah, so this is your, okay, this is your superheater. So this is your basically reheat cycle. Okay, so if you see here, one case is where you are moving from 1 dash to 2 dash, right? One case is you are moving from 1 dash to A and then from 1 double dash to 2 double dash, right? So this becomes your numerator and this becomes your denominator. Okay, so this is your reheater. All right. So this was your question number 1. Okay. So this statement is correct. Okay. So this is the definition of your reheat factor. Then moving on to next question. Whether this is correct or not, please try to answer. Please read it and try to answer. So blade velocity increases with radius from tip to base of blade, whether this is correct or not. So this is question number 2. So I'll just draw. So let's say this is your shaft. Okay. This is your rotor. Okay. So I'll just draw one plane, okay, from the front or lateral if you want to call it. So it is moving in this direction, okay? It is moving in this direction. So one blade I have like this, okay? So this is your basically blade, right? So this is your base of blade, this is your tip of blade, okay? So when we draw this, right? I hope there is no doubt in imagining a blade. So when we draw this, right? So this is basically the cross section of this here. Okay, from the top, if you see, so this is the cross section. The cross section will look like this. Okay, and in reality, this has the blade has a length, right? With this cross sectional shape, this has length from base to tip. Okay. So if it is moving with some angular velocity omega, right? So this is our base and this is your R tip, right? So V tip is RT omega and P is RB omega, right? So obviously V tip is greater than V omega, right? But when we that is what I was discussing earlier. So when we draw our velocity diagrams for our blades, sorry, in that case we take a single blade velocity, but in reality the situation is different. But anyways, to represent our blade, what we do is we take one mean velocity of these velocities from base to tip. Okay. So blade velocity increases with radius from tip to base. So it does increase from with radius, but not from tip to base, from base to tip. So this is false statement. Okay. So this is your question number 2. I hope there are no doubts in it, and if there are, you can just type your doubt in the comment box, and I will answer your doubts there only. So please see this question, read this question and see the options, and please try to answer that which of the following is a correct option to this question. So the question says that which of the following is not a not a cause of losses in steam turbine. So whether this is fluid friction, no, fluid friction is the major cause of losses. Leakage, no, leakage is the cause of losses, right? We have seen it in reaction turbines very well. Then supersaturation. Supersaturation is recently we have seen, right? That supersaturation somehow leads to reduction in the available energy. Then is your superheating. So whether superheating cause losses. So this is the odd one out, right? So the answer to this question is D. Okay. So in our discussion, nowhere we have seen that superheating leads to losses, right? And in addition, we do superheating to improve our Rankine cycle, right? So D is the correct option to this question. So this is question number 4, which says that labyrinth packing in steam turbines is used to avoid what? So this is that kind of question that if you know, you know. If you don't know, you don't know. Okay. But you can try to guess from the word packing, right? So in our steam turbines, to avoid leakages, we use this type of packaging, right? So the correct answer to this question is leakage, right? So in your steam turbines to avoid leakages, we take help of this type of packaging. Okay. Then we have a numerical question. So yes, have a look at the question, what it says. Then we'll try to answer this. So the question is like this. It's a four-stage velocity compounding. So we have seen this in previous week's content, but we have one question based on this. So it's a four-stage velocity compounding. So velocity compounding we call as Curtis turbine also. And we want maximum work ratio, right? And we have the absolute fluid velocity. Okay. So I believe it says that we have first if the if it is moving in single stage only, right? Then the optimum blade velocity for the four-stage Curtis turbine is. Okay. So maybe I'll put it this way only, that this is your absolute velocity. Okay. Velocity at inlet, right? And then we'll try to solve this, right? So we have seen in the lectures, this is question number 5. So if your absolute velocity is this, right? Number of stages is 4. then VB optimum is Vs1 cos theta divided by 2n, right? This. So we can work this out. But before that, let me confirm one thing. Okay. All right. So I have some doubt in this numerical. So maybe I believe I'll not take this in this session. But then, okay, we'll move on to next numerical, right? Maybe I can discuss this in next tutorial. Okay. So this is your question number 6, which says that your Parsons reaction turbine with 4 pair of blades in a group is used in steam power plant, right? So the mass flow rate of steam is 3.2 kg per second, and then enthalpy drop in moving blades is 10.4 kilojoule per kg. So the total power developed by the turbine is. So this is Parsons turbine, which means your degree of reaction will be 1 by 2, which means your enthalpy drop in moving blades will be equal to enthalpy drop in stationary blades, correct? So this is your Parsons turbine. So for moving blades, the enthalpy drop has been given, right? And then mass flow rate has been given, and we want to find the power and the number of pairs have been also given, right? So question number 6 solution. So n here is 4, right? Mass flow rate has been given. Delta H of moving blades is given as this, and then delta H of stationary blades is equals to delta H of moving blades equals to 10.4 kilojoule per kg, because it's Parsons turbine and the degree of reaction of it is half, 50%. Okay. Then power developed in all the four stages is N into m dot into delta H mb plus delta H sb. Okay, so this is 4 into 3.2 into 20.8, right? So calculate this. So if you calculate this, it will come out to be 266.24 kilowatts. Okay, so this is your question number 6. This. Then we have lecture number 11 on steam nozzles. So nozzles are also very important from the perspective of discussion of vapor power plants. So let's see the topics one by one. So the topics we have are, first is area change and flow properties, then Mollier diagram for isentropic flow. Then we have effect of area change on flow properties, right? Effect of area change on flow properties. then expansion process, then compression process, nozzle shape, then critical pressure ratio. So these are the topics. This is your lecture 11. Okay. So what does area change do? So if you see, if you take a convergent duct, okay, so flow is moving in this direction. So I'm showing you one cross section. Okay. So this is your convergent duct. So as the fluid moves in a convergent duct, so if it is subsonic, in that case, the fluid will accelerate as it moves in this duct, right? And with increase in your velocity of the fluid, the pressure drops, right? So this is your convergent duct. Then opposite to it, sorry, is your divergent duct. Where if your fluid is subsonic and it is moving in this divergent duct, in that case we will see compression, right? In here we will sorry, yes, here pressure will reduce and here pressure will increase, right? Here pressure will reduce and velocity will increase. So this is expansion. Here, if a subsonic fluid enters, then the fluid will further reduce its velocity, but pressure will increase. That amounts to compression. Okay. Then subtopic here is Mollier diagram for isentropic flow. So Mollier diagram for so which is HS diagram. So we will draw two constant pressure lines. Okay. Let's say this is naught and this is 1. So this will be H1 and sorry. So this will be H naught, this will be H1 and this will be C1 square by 2. Okay. So if you have to compare state 1 and state 2, comparing state 0 and 1. Okay. So enthalpy plus C naught square by 2, H1 plus C1 square by 2. So initially, if your C naught is 0 and we have the fluid in static state, in that case, this becomes, okay, this expression we get. So, which you also can see on the Mollier diagram, right? So difference between the two states in terms of enthalpy is C1 square by 2. So this is what we call as expansion in this direction, right? This is expansion. And if we move in opposite direction, then it will be called as compression, right? Okay. After that, so expansion, compression, I have discussed. Then is your nozzle shape. So I'll draw a CD nozzle. Okay. This is your inlet. This is your outlet. Right? This is your throat with minimum cross-sectional area. Right? Shape. So this is a CD nozzle, where CD stands for convergent divergent. Right? And one graph also has been given here. So maybe I can draw that. So this is for your area. So this is your length, okay, along the axis of your nozzle. This is the length, right? So along the y-axis, we have taken three things. One is area, then velocity, and then specific volume. Okay. So this area where the area is minimum is throat. So I have not drawn it directly corresponding to the above diagram, but that is fine for our discussion, right? So what basically I want to discuss here is that in your convergent section, that is this section, right? From 1A 2. From 1 to A, you have your convergent section, right? From A to 2, you have your divergent section. So if you see from 1 to 2, your velocity is continuously increasing, right? And then at point A, that is throat, it further first it chokes, right? At throat, your flow chokes, and eventually this becomes sonic at throat, the flow, and then further it expands and the velocity further increases, right? So this is about velocity. But if you see specific volume, so initially the specific volume won't increase drastically, but when we move across the throat, then in case we see drastic changes in the specific volume, right? In case of fluids. Okay, so this is your diagram that has been discussed under a nozzle shape. Okay, then energy balances have been given in this topic, right? So you can refer to the lecture content for that, right? And from there, what we have received is your area to mass flow rate. This expression we have received. So I'll just give the link to the lecture 11 in the description so you can see how this has been presented there. Okay. Okay. Then next is your critical pressure ratios. So what is your critical pressure ratio first of all? So critical pressure ratio basically is the ratio of pressure at throat to the inlet pressure. Okay, so this is your critical pressure ratio. It is also the pressure at which your throat chokes. Okay, by the word choke, I mean beyond this, the mass flow rate of the nozzle cannot further increase. So this is the maximum mass flow rate that a nozzle can attain. Okay, so that is the meaning of choke. So in terms of gamma, that is ratio of specific heats, we can write it as, so this has been derived gamma by gamma minus 1. Okay, so this is for your pressure ratio. For your temperature, the expression is this 2 by gamma plus 1. For pressure ratio, this is 2 by gamma plus 1 raised to power gamma divided by gamma minus 1. And for your critical pressure ratio, this is this. Okay. Then we have expression for velocity, critical velocity at thrust also. Sorry, throat, not thrust, at throat. So this can be given as gamma RTC. Okay. So fundamentally, on the basis of enthalpies, it can be written as 2H1 minus H, where H1 is for your inlet. Okay. Right. Like this. And this can be written as like this. So this is a critical. This. And this can be derived to give this. Okay. This can be derived to give this. So this is your critical velocity at throat. Now, questions based on this lecture. So we shall take, before dealing with this question, we shall take 1 5 minutes break, and then again we shall start with our session, the remaining part of this session. So we can continue with the session. So question number 7 says that when a fluid is decelerated in a duct, causing a rise in pressure along the stream, the duct is called as a what? A nozzle or diffuser. So there are two actions. One is nozzle action, one is diffuser action. Nozzle action basically is to increase the velocity of the fluid, right? And the diffuser action is to reduce the velocity of the fluid. In your nozzle action, your pressure will drop, the expansion will take place. And in your diffuser action, the pressure will rise, that is, compression will take place. So, the correct answer to this question is diffuser. Okay, diffuser action. Then moving on to next question. So four options are there. Please read the question first and try to answer. So in the process of expansion in a nozzle, the the enthalpy drops and the flow velocity dash. So when the expansion in a nozzle takes place, what happens to enthalpy and which type of enthalpy is it? And what happens to flow velocity? So that you have to answer. So four options have been given. So whether this is static enthalpy, whether this is dynamic enthalpy, whether the flow velocity increases, whether the flow velocity decreases. So the expansion process leads to, we have discussed, increase in flow velocity. So two options are there, this and this. So which enthalpy drops, whether it's dynamic or whether it's static? So it's static enthalpy. Okay. By yes. So the fluid that is at rest, right? The static is related to that. Fluid is in motion is the dynamic, right? So when we say H1 plus C1 square by 2, right? So C1 square by 2 here is dynamic part. Okay. So here the static enthalpy drops, and the flow velocity increases. Right? So the correct answer to this question is A. So moving on to next question. So the critical pressure ratio in a nozzle for air is critical pressure ratio PC by P1, where 1 is inlet, is 2 by gamma plus 1 over gamma by gamma minus 1. For air, gamma is 1.4. So let's see question number 9. PC by P1 is 2 by gamma plus 1 over gamma by gamma minus 1. That is 2 by 1.4 plus 1 raised to power 1.4 divided by 0.4. That is 2 by 2.8 raised to power 1.4 divided by 0.4. So work this out. Okay. So this comes out to be 0.52828. Okay. This. So this is your critical pressure ratio. So if you see your options, option D is the correct option. Okay. So this was your question number 9. Then moving on to question number 10. The critical temperature ratio. So critical temperature ratio is this. Gamma is 1.4, so 2 by 2.4. That is 1 by 1.2. 12. So 0.12 8s are 96. 12 3s are 36. 12 3s are 36. 12 3s are 36. Okay. So option C is correct. Okay. So for your question number 10, option C is correct. Okay. Then we have next question. So please read this question. So this question says that find the critical temperature of air at nozzle's throat. Sorry, if the critical velocity is this. So critical velocity has been given. We need to find out critical temperature. So this was question number 11. Critical velocity 340.2 meter per second. We know gamma RTC. Gamma is 1.5 for air. R is 287 joule per kg Kelvin. Right? So 340.2 is equal to 1.4 into 287 into TC implies square implies TC equals to 340.2 square divided by 1.4 into 287. So if you solve this, please calculate this. So this comes out to be okay. So this is your question number 11. So B option is correct. So these were questions based on lecture number 11. Lecture 12 again is on nozzles, steam nozzles. So the topics, so nozzle shape is from previous lecture, then mass flow rate and choking of nozzle has been discussed. So I have briefly discussed what is choking of a nozzle. So design pressure ratios for nozzle, and nozzle performance indicators, then how do we use these nozzles for the expansion of our steam. Okay, then is your super saturation. So we still have around 32 minutes left in this session, so we can move slowly. Lecture number 12. So I'll start from mass flow rate and choking of nozzle. Okay. So we have understood this by means of a, sorry. So we have understood this by means of a convergent duct. Okay, so this is your inlet, this is your outlet, this is your initial pressure, this is your exit. Okay, so this is basically your back pressure. P1 is your inlet pressure. So we have discussed critical pressure ratio, right? That is 2 by gamma plus 1 over gamma by gamma minus 1. So if your PB, we are discussing convergent duct at present and not a CD nozzle, right? So please keep that in mind. So if your back pressure is less than your critical pressure, in that scenario, we will have a choked duct, right? But if your PB is greater than PC, in that case, your duct will not be choked. It means it can further expand if we reduce the back pressure, right? So, in terms of convergent duct, this is discussion on mass flow rate and choking of nozzle, right? So, if your duct is choked, it means your mass flow rate is maximum. So, based on back pressure, this discussion was right. Okay. So, in terms of diagram, if you see, so I'll take a reference of the above drawn convergent nozzle or convergent duct to discuss the pressures related to. Okay, so this is your place. So here we have pressures. Here we have lengths. So this is along the axis of the nozzle. So this is your PB equals to back pressure equals to critical pressure. Then one place we will take where PB is greater than PC. Okay. Then one place we will take where your back pressure is less than critical pressure. Okay. So when your back pressure is equal to your critical pressure, so that is your ideal condition, right? So ideally we want uh, our convergent nozzle to expand in this way when your back pressure is equal to critical pressure. But if your back pressure is greater than your critical pressure, in that case, you won't have your nozzle choked, and the mass flow rate will not be maximum, right? And that is this case. And if your back pressure is less than the critical pressure, in that case, though the mass flow rate will be maximum, but after exiting the nozzle, the expansion will be quite uh, violent, right? Where a series of expansion and compression basically will take place. So it will not be purely expansion. right? So this is what your lecture says on your convergent duct, right? Then is your CD nozzle. Then is your so first I'll draw. So this is your inlet, this is your outlet, this is your throat. Okay. This is your throat. So let's take a reference of this diagram to see in terms of pressure how things are. So along the y-axis we will have pressure. Along the x-axis we will have length, right? So first have this reference, which is your back pressure is equal to pressure at exit. Then is your PB is less than PR. Okay, so the cases are as were discussed in your conversion duct. Okay, so this is your PB is greater than PR. Okay, so here in the above case, we were using critical pressure in place of your exit pressure, because we were using section up to this only. This was section we were using in the above case, but here we are using a divergent section also along with a convergent section, right? So in that case, how the things behave. So this has been discussed here, right? So if your pressure starts from here, right? Okay. So one is the case where your flow is not choked, right? So this is here, no choking. Okay. Because the flow is not choked, in that case, you can see in the divergent section, your pressure is further increasing from the throat only, right? But then there is one another case where you will see that it will cross, right? So it will cross the throat and your pressure is still reducing. That is, your fluid is still expanding, right? After even passing through the throat, it means your throat is choked, right? But what happens is your back pressure is not sufficient, right? At some point here, right? Because back pressure is high in comparison to your exit pressure. In that case, this recompression, right, will take place. Sorry. Right. Then there is one more case where up to this mark, right? Up to mark B, it will follow the same path, but then it will move in this direction. So this is your when your back pressure is equal to your exit pressure, right? So this is your basically design case, ideal case. Then if your back pressure is less than your exit pressure, right? In that case, again, there will be series of expansion and compressions. So that is your last case, right? So this, when your back pressure is greater than your exit pressure, this is called overexpanded case, right? And when is your uh, back pressure less than your exit pressure, then it is called underexpanded. Underexpanded means it has still has the capacity to expand, right? And overexpanded means we cannot further expand it. All right. So this is your discussion on CD nozzle, right? Okay. Then next topic is your nozzle performance indicators. So, so I'll first draw HS diagram for nozzle expansion. So this is your isentropic case 1 to 2. Okay, so I had lost internet connection because of a short power cut. But anyways, I'm back. So I was discussing nozzle performance indicators, right? So I have drawn the Mollier diagram for the expansion that takes place in a nozzle. So 1 to 2s is your ideal case, that is isentropic case, and 1 to 2 is your real actual case, right? So the performance indicators that we use to have the performance, indicate the performance of nozzles. One is your nozzle efficiency. So nozzle efficiency is your enthalpy drop by enthalpy drop isentropic, right? So this is your nozzle efficiency. Then is your velocity coefficient. So your velocity coefficient basically is so the velocity that is achieved at the exit of the nozzle, right? And in the actual case and in the isentropic case. So when we take the ratios of these two, so we get the velocity coefficient. Then there is coefficient of discharge. So what is coefficient of discharge? Coefficient of discharge basically is the ratio of mass flow rate in actual case to the mass flow rate in the ideal isentropic case, right? So this is your coefficient of discharge. Okay. Then there is discussion of supersaturation. So supersaturation we have discussed, but there are two parameters that we can discuss, or I can just jot down. So some expansion is taking place from 1 to 2, right? So from A to B, point B, this is super saturated region, right? Where the condensation doesn't take place. But then here, what is degree of supercooling? Degree of supercooling, because the condensation is very rampant. That is why we are using it. Okay. So T2 is temperature at 2 and TB is temperature at B, right? Point B. So this is your degree of supercooling. Then is your degree of supersaturation. That is, sorry, B, right? This pressure and the pressure at point B. So this is your degree of supersaturation. So these are two parameters linked to supersaturation. Okay. Then moving on to the questions. So the question says that in a convergent nozzle, as the back pressure is reduced beyond critical pressure, the mass flow rate dash. So the question talks about a convergent nozzle, and then back pressure is reduced beyond critical pressure. The what happens to mass flow rate? So we know that if the back pressure goes beyond critical pressure in a convergent nozzle, in that case, there is nothing that happens to mass flow rate, right? So it will remain unchanged because up to critical pressure only. If we reduce the back pressure, the mass flow rate will increase. But beyond that, there is no change in mass flow rate. Okay. So C is the correct option to this question. Then we have question number 13. So it says that a nozzle is said to be underexpanded if the back pressure is below the design value. So this is a false statement. So back pressure is below. So if you see this diagram, so back pressure here is below, if the back pressure is below the exit value, in that case it will be underexpanded, right? But if your back pressure is above the exit value, in that case it will be overexpanded, right? So this is a false statement. Sorry, this is I believe a correct statement, because a nozzle is said to be underexpanded if the back pressure is below the design value. So this is a correct statement, right? So this is a correct statement because your back pressure is less than the design value. Okay. Then is your question number 14. That is, I believe, the last question of the session. So this says that the ratios of specific heats for dry, saturated, and superheated steams are dash and dash respectively. So for dry saturated, the specific heat is, and for your superheated steam, this is 1.3. Okay, so if you see the options, so C option is the correct option. Okay, so this was it about your tutorial number 5. So I'll conclude the session. So there were 3 lectures based on your vapor power system, and the whole discussion revolved around nozzles. Initially, we saw the performance analysis of steam turbines, where we saw different losses that are witnessed in a steam turbine, right? By means of through leakage, right? Through supersaturation, through friction, right? So, and there were miscellaneous losses also, like mechanical losses. So all this was discussed in your lecture 10. Then we moved on to lecture 11 and 12, which were on nozzles. So nozzles basically are to expand your fluid, right? So in our case, we are discussing nozzles because we want to expand our steam, right? And then we saw 2 types of nozzles. One was your divergent with divergent duct, and then one was your CD nozzle. And then we saw the concept of back pressure, right? And then critical ratios, critical pressure ratios, critical temperature ratio, your critical velocity at the throat, right? And how they are related to your gamma, that is ratio of specific heats. So this was discussion on your nozzles, right? So this was it about this session. Thank you for watching this session, and we shall meet again in the next session, that is session number 6, on the coming Tuesday with same timing, that is 6 to 8 p.m. So till then, bye, and thank you for watching. Thank you.